So we explored one greedy algorithm in the context of scheduling. Let's look at another one in a similar type of problem. So remember that a greedy algorithm is one that makes locally optimal choices. So we are trying to achieve some global optimum. We are trying to achieve some minimum or some maximum overall. But we proceed step by taking local choices. And at each local choice, we look at some local measure or some local cost or some local distance or some local time and choose something which is optimal right now, and we never go back and examine this choice again. So the real difficulty is to justify that the strategy that we use to make these local choices is actually optimal. So in our first scheduling algorithm, which was interval scheduling, what we wanted to ensure was the maximum number of requests for these resource were satisfied. And we came up with several heuristics which we could show were wrong by giving counterexamples, and finally we came up with a greedy strategy which says that we should take the earliest finishing time as the next job to process. Now when we did this, what we said was that the optimal solution need not coincide with the solution that our greedy strategy gave, because there could be different subsets of jobs which satisfy this criterion of being the total number of jobs scheduled being the maximum. So since we can't directly argue that the optimum solution is equal to the solution of the greedy algorithm, we had an incremental approach by which we said, okay, if we order the jobs in the sequence in which they appear in the schedule, then we can show step by step that at step k, the greedy algorithm always stays ahead in time. So it is always doing better than any optimum solution that you could give. Right? So this was one strategy that we used to show that a greedy algorithm performs optimally. Now today we will look at a different type of problem where actually the two solutions are comparable. That is, you can take the solution of the greedy algorithm and you can argue that any optimum solution must also have a similar structure, and then we will show that we can prove optimality by taking the optimal algorithm and transforming the structure from that into the greedy algorithm so that the two have the same structure, and this transformation will not violate optimality. So if you start with an optimal solution and you keep making transformations which preserve optimality, and you eventually reach the solution of the greedy algorithm, and the greedy algorithm itself has produced an optimum solution. So as I said, this is another scheduling problem. So in the earlier case, we were talking about a lecture room where faculty wanted to record lectures, and they said they gave preferences in terms of times when they wanted to come, and we wanted to allocate the lecture room so that two faculty who came to use the lecture room and had an overlapping timing could not be allocated at the same time. Here we have a different type of resource constraint. So let's suppose we have a resource like a 3D printer. So different people want to use this 3D printer. So there is no fixed time that they use it at, okay, but each person has a different type of requirement. So they want to print some object, and this 3D printer takes different amount of time. So each user I requires the printer for time Ti. And though they don't have a fixed time interval when they want to use it, they do have a deadline. So they want to complete and have their object ready by some deadline D of I. Right? So each user has a time required for that person's job, T of I. The user has a deadline D of I. Now in the earlier scheduling problem, we said we would only allocate a subset of the users, those who do not contradict each other's timings. Here on the other hand, we are going to make sure that everybody is actually allowed to use the printer. But what we want to minimize is by how much they miss their deadlines. So each user starts at some time, and because the time that the print job takes is fixed, right? So you have this T of I, right? So the time that the user will finish is guaranteed. If they start at S of I, then they will finish at F of I, which is the start time plus the time taken by the task that the ith user has for this printer. Now our goal of course is that the ith user should finish before their deadline. So we would like F of I to be less than or equal to D of I, but it could be that F of I exceeds D of I, in which case this user I is late. The user I has missed their deadline, right? So there is a lateness for I, L of I, which is the finish time minus the deadline. If that finish time is after the deadline. If it is before the deadline, then this thing would be 0. We would not take it as lateness being negative. So you would only use this when the lateness is positive, when the finish time is after the deadline. So what we want to compute is how bad is this across all the users. So we are not trying to add up the lateness of all the users, but rather say which user has been delayed the most. So we want the maximum value of Li over all the users who are trying to use this resource, and our goal is to minimize this maximum, right? So we are not again computing the sum of all the lateness. We are saying take each user and see how late that user is, and we are trying to minimize this maximum, right? So this is our goal. So we want to schedule these resource allocation for this printer in such a way that we minimize the maximum lateness. So like the earlier scheduling thing, we could come up with many heuristics which seem reasonable at first sight. So first thing would be to try and finish off short jobs earlier so that people don't get delayed, right? So you can schedule requests in the ascending order of the expected time that it takes for that job. Remember, we know we have a prediction T of I saying that the ith job will take exactly T of I time. So we sort the jobs in terms of this and do the shortest jobs first so that people are not unnecessarily waiting. So unfortunately, we can construct a simple counterexample where this does not work. So here it is. So we just have two jobs. We have one single job which requires only one time unit, and we have a job which requires 10 time units. So we will always assume that we start at time equal to 0. So we are measuring this in some unit, hours, minutes, days, it doesn't matter. So at time equal to 0, if we allocate the first job, right? So at time equal to 0, then at time equal to 1, it will finish. So this will be job 1, right? And then at time equal to 11, the second job will finish because it's going to take 10 time units. Right? As a result of which the second job has got delayed by 1 time unit with respect to the deadline because the deadline was 10. So this is not a good allocation, but obviously you can see that if you reverse this allocation, because the first job, though it takes only 1 time unit, has a very relaxed deadline. So instead what you should do is you should allocate job 2 first and finish it on time so that there is no delay, and then in the next time unit you can finish off the first job, and its time delay is not at all in question because it can afford to wait till time 100. So therefore picking the smallest time job first is not a good strategy. Here you would like to pick the larger time job. So this is not a good algorithm. On the other hand, you can ask, so here we have a kind of tight deadline, right? So this job takes 10 units of time and it must finish by time 10. So that means that there is not much flexibility to move this job back and forth, right? Whereas this job has a lot of flexibility. It requires only 1 time unit, but it can finish any time up to 100, so you can move it up and down a lot. So you can look at this difference, how far away the deadline is compared to how long the job is going to take, and that gives you a measure of how flexible the scheduling of this job is, how much you can move it up and down. So what we might argue is that those which are inflexible, like this one, right? So this one I don't have really much, I don't have any flexibility. If I want to finish by the deadline, I must start it right away. So we can start with those requests which have the least flexibility. So the least slack time. The slack time is the amount of time that I have to play with between the deadline and the time that the job will actually take to finish, right? So supposing I give priority to jobs with smaller slack time, then would this work? So again, as you might expect, we can come up with a counterexample which is sort of similar to the earlier one, except we move this deadline down to 2. So now let's see what happens, right? So if we take the smaller slack time, then we do this first, right? So then we have this thing is delayed by, it finishes in time 10, so this is job number 2 finishes at time 10, and then job number 1 finishes at time 11. But with respect to the deadline of this job, right, the deadline was 2 and it finished at 11, so the cost is actually 9, right? For job 1, the cost turns out to be 9 in this case. On the other hand, if you did it the other way, that is you pick the job which had some flexibility first, then you would finish the first job in time at time 1, sorry. So it would not incur any penalty. And then you would take up the second job, right, and it will finish at time 11, but now the deadline has only been violated by 1. So the lateness of job 2 is only 1, right. So by taking it in the order where you take the one with more slack time earlier, you actually incur a smaller penalty in terms of lateness because the deadlines were later. So neither of these strategies actually works, and in both of these cases we have come up with specific counterexamples. Now the reason to go through these kind of arguments is to show that it is very tempting to come up with greedy strategies which sound plausible. But when you come up with a greedy strategy, as we have seen, what you need to do is justify that it works, and that's the whole purpose of this exercise. Okay, so let's look at a third strategy. So the third strategy says, okay, instead of asking which jobs can finish first or which ones are most flexible, which jobs take the least time or which jobs are most flexible, let's ask which jobs are the most urgent, right? So which jobs have the earliest deadlines, which are the ones that we must do first. And it turns out that this actually works. Okay, so we actually schedule the jobs in the order of their deadlines. So when we do it in order of deadlines, we are ignoring how much time it takes for that job. We are also ignoring how much slack we have between them. We are just looking at when the job should be finished. Now, if you think about the way that if you have a lot of commitments, this is one way to process your list of to-do things, right? Which are the things which I have to do by tomorrow, which are the things I have to do by day after tomorrow, and so on. So it is sort of natural, but why is this more or less natural than the other is not clear. And why should it work? Well, it does work, and our goal is to prove that it works. So what we are going to do is very simple. We are going to take all the requests that have come. Okay, these are print jobs on this 3D printer, so we call them jobs or requests. So we take all these jobs and we will now sort them by their deadline. Okay, so remember, D of I is the deadline, T of I is the time it takes. So we sort them by the deadline, so that the numbering is such that the jobs 1 to n, job 1 has the earliest deadline, job 2 has the next deadline. Now you might be multiple jobs with the same deadline, we don't rule that out. So all we know is that D1 is less than or equal to D2 is less than or equal to D3, and so on. It is possible that they all have the same deadline, it's possible they all have distinct deadlines, but they are arranged in increasing order of deadlines. Now once we do this, the algorithm is very simple. The schedule is just because we are going to schedule everybody. Remember, it's not like the earlier interval scheduling case where we have to pick out something and then we have to remove all the conflicting things. Remember there, if we allocated person I to take the room, then anybody whose slot conflicted with I had to be removed from the set of possibilities. Here there is no such thing. Everything is possible, it's just a question of delay. So we just, once we sort this in terms of deadlines, we are just going to allocate it in that same order. So once we have got the sort, we have got the allocation, it's just 1 to n. So in this allocation, job 1, that is the one with the earliest deadline, starts at time 0 and it goes on till time t1, right? T1 is the amount of time job 1 takes. So S2, the second job, starts at the time that the first job finishes, which is T1. So S2 starts at F1, right? And then F2, the time when the second job finishes, is F1 when it starts, S2 when it starts plus the time it takes, right? S2 plus T2. Similarly, if I have finished Fk, then the next one will start at Sk will be equal to Fk, and then it will be Sk plus Tk, right? So in general, the last job Sn will start when the n minus 1th job is finished, and it will finish at time Fn, which is Sn plus Tn, right? So this is a simple algorithm, but what we have to justify is that this way of doing it works. So one thing to observe is that when we do it this way, we are not having any gaps, right? There is no idle time. There is no time when the printer is not being used, because as soon as the first job finishes, we start the second job. As soon as the second job finishes, we start the third job, and so on, right? So our printer is being used continuously from 0 to f of n, right? And the claim is that this is in general a good strategy. That is, there will always be an optimum schedule in which there is no idle time. Now, why will there be an optimum schedule in which there is idle time? Well, you could have very large delays. So supposing I have 2 jobs, each of which take only time 1, and each of them has a deadline of 100, then I have many different ways in which I can schedule them. I can wait and put them, after time 99. So one at 98 and one at 99, and I will still finish within the deadline. Remember that if we finish within the deadline, we don't count the lateness. So we are not asking anything about jobs which finish ahead of the deadline. So there could be optimal schedules with idle time, but we are saying that there will always be an optimum schedule without idle time. And that's very easy, because what happens if you have idle time is that you have your job here, and at some point this is your job allocation, and there is a period in between when nobody is using the printer. Well, if I just take this entire segment and move it to the left, then obviously everybody will finish earlier than they had finished before. So therefore, if they were late, they will be less late. If they were not late, they will not be late now as well. So it can only reduce lateness, right? So compressing a schedule with gaps into a schedule without gaps by moving all the gaps, reducing the gaps by moving everything left, can only reduce the lateness. So if I have an optimum schedule, as I said, if I have this stupid example where I have a deadline of 100 and I have 2 jobs which take time 1 each, and I decide to allocate them here, right, at 98 and 99, then I can take this whole thing and shift it left and allocate them at 1, 2 and finish them off, right. So this is what we mean by saying that there will always be an optimum schedule with no idle time. So it's sufficient to look in that space. So what we want to argue is that our greedy solution is optimum, and like last time what we have to do is compare it to an arbitrary optimal schedule. So there are many optimal schedules we could compare it to, but we will only compare it to optimal schedules which, like our solution, has no idle time. So now let's look at correctness, right. So as before we said, look at an arbitrary optimal schedule. So let's look at an arbitrary optimal schedule O. So we have a schedule which our greedy algorithm produces, which we're sorting and just saying 1 to n, right. So remember, the numbering has been fixed by our sorting. So what we are going to show now is that, now notice that any schedule has to schedule all the jobs. It is not like the earlier case where the optimum schedule could have given a subset of instructors the lecture room, and my schedule could have given another subset. We just had different subsets of the same size. It's not like that. The optimum schedule here is going to have exactly the same indices 1 to n, but in a different order. So what we are going to argue is that we can take the sequence in which O allocates this printer and transform it into something which looks like 1 to n without changing the optimality of O. So notice that in our schedule, if a number 2 appears before number 3, it means that the deadline of 2 is before deadline of 3, right. So that is the property that we add for this numbering. So in our schedule, there are no inversions. An inversion happens when I appears before j, but the deadline of j is actually earlier than the deadline of I. Remember, now the numbering is already in some sense reflecting the sequence of the deadline. So obviously by construction, we cannot have an inversion in our greedy schedule. But this optimum schedule could have, anytime you have something which is different from the greedy schedule, it will mean that there are 2 indices which are in the wrong order. And if they are in the wrong order, then necessarily it must mean that the later one has something which is, not necessarily, but in general it will mean that the later one has a deadline which is earlier than the previous one, and therefore it should have been done in our greedy schedule in the opposite order. So now first look at a solution in which there is no idle time, which we have already argued must be the case, right, and there are no inversions, but they are different. Now how can 2 schedules be different but have no inversions? Well, the difference can happen because I have equal deadlines. So when I said before that we do not assume that the deadlines are distinct, right, I could have that di is less than or equal to dj, and actually in fact or di plus 1, let us say, just say 2 adjacent things, in fact this is equal to. So our greedy algorithm chooses one order, it chooses I and then I plus 1, but maybe the optimum schedule chooses I plus 1 and then I. So then these 2 would be different schedules, but there is no inversion, because inversion says that the later one must be strictly earlier in deadline than the previous one, right. So it's an inversion only if the one that appears later has an earlier deadline, not an equal deadline. So therefore, if I have no inversions and no idle time, the only difference can be in the order of request with the same deadline, right. So what we have to argue is that this doesn't matter, that they all produce the same maximum lateness. So any reordering of jobs which are next to each other with the same deadline is not going to create a problem. So let's look at the situation. So supposing we have at this point, right, so we are here maybe, and now we have the next 3 jobs in our list have the same deadline, which is this. And our schedule, the greedy schedule, produces this order, the green one followed by the yellow one followed by the orange one, and the actual deadline is somewhere here in the middle of this yellow patch, right. So this is the actual deadline. And let's assume now the optimum schedule, it cannot invert, but it can reorder this, because it will not be an inversion in the sense that we have defined it, because they are greater, they are all equal. So let's assume the optimum schedule actually does yellow first, then orange, then green, right. So the relative lengths of these segments is the same because it's the same job, but it's just that the sequence has been shuffled. But notice that in the sequence shuffling, the total time it takes is the time for the green job plus the time for the yellow job plus the time for the orange job in whatever order I take. So if I look at the beginning and if I look at the end of this group happens at the same time as it does in the earlier case. So if I look at the lateness of the maximum lateness, then it is determined by the difference between the end of the green job now and the deadline, which is the same deadline for all of these. So earlier the orange job was the witness for the maximum lateness. Now the green job is the witness for the maximum lateness. So which job is being delayed is changing, but the amount by which it's being delayed is not changing, right? So any two schedules with no inversions and no idle time have the same maximum lateness. So shuffling around things with equal idle time does not matter, with equal delays doesn't matter. So now we want to argue that there is an optimum schedule with no inversions and no idle time. Okay? So our schedule, the greedy schedule, is such a schedule, right? It has no inversions and no idle time. We want to argue that there is such an optimum schedule. So we start with, as before, we start with an arbitrary optimum schedule, but we can always assume that this optimal schedule has no idle time, because as we said, we can always compress an optimal schedule without increasing the lateness, because everything just shifts to an earlier time. So now our problem is that there may be inversions, right? Because we want no inversions and no idle time. So no idle time is okay, but no inversions is not something that we can assume in general about an arbitrary optimal schedule. So if there is an inversion, then I claim that there will be an inversion between two adjacent jobs, because if you start with, so my optimal schedule orders them as I1, I2 up to In, right? So this is some permutation of 1 to n. Now if you start from here, and if I look at d of I1, then it will be smaller than d of I2 up to some point, and then at some point I will, because there is an inversion, there is something later which is earlier. So this deadline which keeps increasing must go down at some point. So if I look at these two, the place where it goes down, the first point where the deadline decreases instead of increasing. In our greedy schedule, the deadline as we go from left to right keeps increasing, right? In a schedule with inversions, it must decrease at some point, otherwise there is no inversion. So if I look at that point where this decrease happens, I am guaranteed that there will be two adjacent things, right, in which the second job has an earlier deadline than the first job. So the inversion is actually between two adjacent elements. Right? So if I exchange these two, so I and j are these two. So the reason they are called I and j is because the numbering I and j is with respect to my greedy schedule, right? So they are consecutive elements in the optimal schedule, but with respect to their job numbering, there are some I and some j, and they come after each other, and j is after I. So I can say, okay, put j before I. Now because the assumption of the inversion is that dj is less than di, right? So if I exchange these two, then this one inversion goes away, right? Because earlier, now this was an inversion, now I swap them. So it's easy to see that the inversion decreases, but what is the property that holds for the lateness, because that's what we want, right? So we can swap these two jobs, but does it affect the optimality of O? So the claim is this does not, right? So it's not obvious, so we have to prove this, that exchanging I and j is the obvious thing to do to remove the inversion, but why does this not make O any worse than it was before? Why does it keep the maximum lateness not worse than what it was before? So this is the picture we have, right? So we come up to some point, right, and then we have these two jobs I and j, such that the deadline of j is before the deadline of I. So let's assume that the things have passed, right? If the deadlines are to the right, there is no problem. So let's assume that the deadline has passed. So the deadline of j is like this. So we have this delay between the deadline of j and the time that j finishes. So this is the lateness as observed by j. Now I am going to exchange these two, right? In the process, the lateness of j is going to reduce clearly, but the lateness of I is going to increase because it is going to go to the right. So what's going to happen, right? So when I exchange these two, now I have a problem with the lateness of I. The lateness of j is no worse than before because it is finishing earlier, right? But what about the lateness of I? Well, the lateness of I is certainly worse than before. So I have to compare the earlier lateness of j and the current lateness of I. But here I have this property, right? I know that the deadline for j was strictly earlier than the deadline for I. So if I look at the difference from this point to the deadline of I, it's going to be less than from here to j. So whenever I do this swapping of adjacent things which have an inversion, I am guaranteed that the lateness due to these two does not change. Now it could be that there is some other job which has a higher lateness, but I am not affecting that job's finishing time anyway. Everything to the left of this and everything to the right of this all finish at the same time as they did before after the swap. This is only affecting the finishing time of INJ. So within INJ, the lateness only reduces. It could be there is some other job which has a maximum lateness which is higher than this, that is unaffected. But if J was the culprit, if J was the maximum, in fact we have reduced it, right? But certainly it is not increasing. So this is the property now that we have shown. We said that we have an optimum schedule. We will find, if there is an inversion, we will find two adjacent elements which have this inversion among them, and we can swap them, and in the process the lateness does not change. So using C, we can remove each adjacent inversion without increasing the lateness, right? Now how many examples of this could there be? Well, every time there is a lateness, it is with respect to some pair I comma j. So there are only as many possible inversions as there are pairs I comma j, and the number of pairs I comma j is n into n minus 1 by 2, right? It's a very simple observation. The number of ways you can pick two elements from n is n into n. So there cannot be more than n into n minus 1 by 2 inversions to start with. So if I just keep repeatedly removing these inversions without affecting optimality, I am gradually moving from O towards a schedule which has no gaps, no idle time, and no inversions, right? And once I finally do that, right, so ultimately this must be the schedule that we have in our greedy algorithm. Our greedy algorithm has this property that it is defined this order, so it has no inversions by construction and no gaps, and I have taken an arbitrary optimal schedule and done this exchanging. So this is called an exchange argument. By exchanging components of that solution, I have gradually transformed it into the solution that I have, right? So this is proof that any optimum schedule can be converted into a schedule which looks like our greedy schedule, and since this conversion does not affect optimality, our schedule that we produce because of this greedy algorithm must be optimal. Right. So to summarize, we have a simple situation here where we have one resource, right, and we have users trying to access this resource, and they don't have fixed time intervals when they want to use it, unlike the lecture hall scheduling, but they do have a requirement in terms of TI of how much time they need, and they have a deadline by which they would like to finish it. And our goal is to minimize the maximum lateness. That is, among all the users who do not meet their deadline, I want to find out what is the maximum slippage of this deadline that I have. I am not trying to add up these delays, but rather just find out by how much does the worst affected user get delayed. So our simple greedy algorithm just sorts the requests by this deadline and then processes them in that order. And what we said is that this is guaranteed to be correct by our exchange argument, and this takes n log n time to sort, and then once we have sorted it, of course the schedule is just the order in which the sorted array comes, so that just takes linear time, right? So this exchange argument is critical, which says that we can take any optimal solution, and then first we made some assumptions that this optimum solution looks a little bit like our thing because it has no idle time, and once it has no idle time, we can keep exchanging these adjacent inverted elements until we eventually remove all inversions, and therefore we must have reached our greedy solution without sacrificing optimality.